All right, this is section 15.2, iterated integrals. Iterated integrals is just a really fancy name for repeated integrals. More than one. All right, so we're going to be able to evaluate iterated integrals using the fundamental theorem of calculus. So in the previous section, we introduced the whole idea behind multiple integrals and double integrals to be specific, but we never really used them. We did kind of Riemann sums in the last section to get good approximations. Well, this time we're actually going to be able to do them using iterated or repeated integrals. So what is the iterated integral? Again, an integral of functions of multiple variables. It is an integral of functions wow, that looks like an ST. It was supposed to be the word of. Something happened here with my pen. I'm not sure exactly what's going on. There we go. Of multiple variables. All right, so how are we going to do that? Well, let's do a couple of integrals with multiple variables in it, but notice that they're each single integrals. So the first one I want to do is the integral from 0 to 3 of f of xy dx. So notice that this is with respect to x. So let's do the integral from 0 to 3 of f of xy, which is 2x plus 3x squared y dx. So we're taking the antiderivative here with respect to x, and then we're going to use the fundamental theorem to evaluate what we have. So the antiderivative of 2x with respect to x, it's just like it would have been before, that's x squared. Then the antiderivative of 3x squared y, remember we treat y as a constant here because we're taking the antiderivative with respect to x only. So that's going to be, let's see, raise the x power by 1, that'll be x cubed, and then divide by the 3, so that 3 in the front is gone, so it's going to be x cubed y. And then we will evaluate that from 0 to 3. Biggest thing is remember what you're plugging the numbers in for. This was with respect to x. We're plugging 3 and 0 in for x. So let's see, we're going to get 9 plus 3 cubed is 27, so 27y, minus, plug 0 in for both of those, you get 0. So really what we get here is 9 plus 27y. And that's the integral of our function of xy with respect to x. Now let's do the same thing, but with respect to y. Except that the integral is going to go from 0 to 4 this time. So remember to treat x like it's a constant. So the antiderivative of 2x, remember that's a constant, is just going to be 2xy. Then the antiderivative of 3x squared y, raise the power of y by 1, that's squared, divide by the square, and you're going to get 3/2 x squared y squared. And we will evaluate that from 0 to 4. And again, the biggest thing is, remember, you're plugging these in for y. So if I plug the 4 in for y, we're going to get 8x. Let's see, 4, and there's going to be 16. 16 times 3/2 is going to be 24x squared. And then if I plug 0 in for y, we get nothing, so that's it. Oops, it's supposed to be in green, whatever. So there you go. There are integrals there of multiple variable functions. What we're going to focus on is we're going to focus on the double integral and how that works. So let's do an example number 2, which for whatever reason I didn't type up. So let's just write in what this was supposed to be. So what we're going to find is we're going to find the double integral, or we're going to set up a double integral over the region that x is bounded from 0 to 4, y is bounded from 0 to 3, and we're just going to do this underneath the plane z equals 2 to make it easy. So if we look at that, if we kind of sketch what that looks like, so the base of our region is that x is bounded from 0 to 4, y is bounded from 0 to 3. So we're going to go ahead and just kind of sketch that. X goes from 0, 1, 2, 3, 4. Y is going to go from 0 to 3. So the base of our region is down here. And it's going to be underneath the plane, z equals 2. Well, that just means that the plane has a height of 2 and it doesn't change. So if I was to actually sketch the region that we're going to go ahead and take this under, it's going to go like something like this. Trying to stay parallel here to the best of my ability. Something like that, where if I were to extend this straight down, you can see that what you have there is a height of 2 underneath the plane. So ultimately, really what we're trying to find is the volume of that. Now, we could obviously do this without doing an integral, but I just want to show it to make sure it works. So you could certainly find the volume of that, volume underneath of that plane. That would just be a length times width times height. So we know what we're supposed to get. But if I want to do the double integral, well, let's see. Let's see. It doesn't really matter in this case which order it is. I'm just going to say let's do the y. Actually, no, this will be the x, sorry. The x is going to go from 0 to 4. And the y is going to go from 0 to 3. And what is it that I am taking the integral of? I'm taking the integral underneath of the plane 2, z equals 2. Excuse me. So according to what we said we're going to do, excuse me, you work these double integrals, you work them inside out. So the first integral we're going to do is the one with respect to x. And that's, make sure you line up your integration, your integral symbols with the appropriate variable. So you work them inside out. Whichever one is first on the inside is also the first variable, so they'll line up together. And then as you can see, the green ones on the outside line up together as well. So we'll take the first one, antiderivative with respect to x is just going to be 2x. And we'll evaluate that from 0 to 4. Don't forget you're still going to have the integral from 0 to 3, dy left over. Fundamental theorem of calculus, plug in the 4 for x and you're going to get 8. Plug in the 0 for x and you're going to get 0. So 8 minus 0 is 8. So I have left over the integral from 0 to 3 of 8 dy. So then if I take the antiderivative with respect to y, I get 8y from 0 to 3. And then evaluating that, plugging into 3, you get 24. Plugging in 0, we get nothing. So 24. And that, again, that should make sense. Because really what we were finding was the volume of that, basically that box, that rectangular prism, which would have been length times width times height. 4 times 3 times 2 is indeed 24. So it does make sense. It works. Good, easy example to show to start with. Obviously, they're not all going to be that easy. Now let's do the double integral from 1 to 3, 0 to 1 of 1 plus 4xy dx dy. So again, the important thing is do the part first that it says to do first. It says to do this part, which is the integral from 0 to 1 with respect to x. So let's take an antiderivative with respect to x. We're still going to have left over the outside piece, the dy part. So that's going to be with respect to x, it'll be x plus let's see, that'll become x squared. Dividing by that's going to be 2x squared y. And we'll evaluate that from 0 to 1. So now remember, you're plugging that stuff in for x. Carry through the other integral. Plugging the 1 in for x, you're going to get 1 plus, let's see, what's that going to be? 1 squared, 1 times 2, so 2y. And then plugging 0 in for the x's makes the x's go away. Wonderful. We don't have to write anything else there. Now we're going to do the second part with respect to y. So the antiderivative with respect to y will give us y plus y squared from 1 to 3. Plugging in a 3, you're going to get 3 plus 9 is 12. Minus 1 plus 1 is 2. So we get 10. So whatever that curve, 1 plus 5xy, looks like over the region in the xy plane where x is bounded from 0 to 1 and y is bounded from 1 to 3, you have a volume of 10. And it might help to, sketch the base just so you have somewhat of an idea, although you don't necessarily have to when it's something that's that simple. All right. This next one's pretty cool because what we're going to do with it. First thing I'm going to do is I'm going to show you just doing the regular antiderivative, how this stuff works. So let's go ahead and do it again. So if we want to do this with respect to y,